Welcome to the deep dive. You asked us to sort of unpack the chi-square test. It's one of those statistical tools you hear about.
That's right.
Our mission today is really just to get the core ideas when you use it, what it tells you, without getting totally bogged down in, the heavy stats.
Absolutely. And first off, it's key to know what kind of data works here. Chi-square is your go-to for categorical data.
Categorical. So, like groups,
Yeah.
things you can put into boxes.
Exactly. Think survey answers like yes, no, maybe, or types of products, maybe even different city neighborhoods. It's about counts within those distinct groups.
Okay, not things like height or temperature then. Those are different tests.
Right. That's continuous data, needs different tools. Chi-square is all about analyzing counts and categories.
Got it. Counts and categories. Now, I know there are like two main flavors of this test, independence and goodness of fit.
Yep, that's the main split. The chi-square test of independence is all about seeing if two categorical variables are, well, related or independent.
Okay, so like, does someone's favorite music genre relate to their preferred social media platform, that sort of thing?
Precisely. Are those two things connected, or do they seem to operate independently? We're testing that association. It helps avoid just assuming a link.
Right. Avoid jumping to conclusions. Okay, so that's independence. What about the other one, goodness of fit?
Goodness of fit is a bit different. It looks at just one categorical variable, and it compares the counts you actually observed in each category
Uh-huh.
to the counts you'd expect to see based on some theory or maybe some known distribution.
Ah, okay. Like, if I expect a die, to be fair, each side should come up, what, 1/6 of the time?
Exactly. You roll it many times, count how often each number appears. The goodness of fit test tells you if your observed counts are significantly different from that expected 16th for each side. Useful for checking if things match a predicted pattern.
Makes sense. Okay, let's circle back to that independence test for a sec. You have your data, maybe in a table. How do you figure out those expected counts you mentioned if the variables were totally unrelated?
Yeah, for each little box or cell in your table, there's a simple formula. You take the total for that cell's row,
Okay.
multiply it by the total for that cell's column,
Got it.
and then divide the whole thing by the grand total number of observations in the entire table.
Row total times column total over grand total.
That's the one. That number tells you what count you'd expect in that specific cell purely by chance if there was absolutely no relationship between the two variables. It's our baseline for comparison.
The no relationship benchmark. I
Yeah.
like that. Okay, what about this term degrees of freedom? It always sounds a bit floaty.
Huh. Yeah, it can sound abstract. For the independence test, it's calculated as number of rows 1 times number of columns 1.
Rows 1 times columns 1.
Right. Conceptually, think of it like this. Once you know the row and column totals and you start filling in the cells in your table, you only have a certain amount of freedom in assigning those numbers before the remaining cell values are kind of locked in to make the totals match up.
Ah, okay. So not all the cells can vary wildly if the totals are fixed. That makes a bit more sense.
Yeah, exactly.
Now, I've heard a warning bell about expected counts being too small. Why is that an issue?
Yes, that's a key assumption check. The general rule of thumb is that most of your expected counts, the ones we just talked about calculating, should be at least 5.
At least 5, okay.
If you have many cells with expected counts lower than that, the math behind the chi-square test starts to become less reliable. The test result might not be accurate.
So very small expected counts in some categories can mess up the result.
They can, yeah. It's like trying to make a judgment based on almost no evidence in that particular combination of categories.
There are fixes.
Like Yates correction or Fisher's exact test, especially for smaller tables. But the standard chi-square prefers those expected counts not be too tiny.
Good to know. So let's say we run the test, we get our chi-square statistic. What if it's a really big number? What's that telling us?
A large chi-square value basically means there's a big difference, a big discrepancy between the counts you actually observed in your data and the counts you expected based on the no relationship or matches the theory idea.
So big number, big difference.
Right. And a big enough difference suggests that the mismatch isn't just random chance. It usually leads you to reject the null hypothesis.
Which is the hypothesis of no relationship or no difference.
Exactly. You'd conclude there probably is a relationship for independence, or the data doesn't fit the expected pattern for goodness of fit.
Got it. Makes sense. So what are the main assumptions we need to tick off before we even run this test?
Okay, Q assumptions for chi-square. First, you ideally need a random sample from your population.
Right.
Second, the observations need to be independent of each other. So one person's response shouldn't influence another's.
Makes sense.
Third, the data must be categorical, as we said at the start, counts in groups. And fourth, that point about sufficiently large expected counts in each cell, usually that at least 5-foot guideline. If these assumptions aren't met, your test results might be misleading.
Okay, crucial checks. And if we want to show these results to someone, how can we visualize them effectively?
Bar charts are often really good here.
Yeah.
For goodness of fit, you could have side-by-side bars showing observed counts versus expected counts for each category. Makes the comparison obvious.
I can picture that.
For the independence test, you could use stacked bar charts or grouped bar charts. They help you see how the distribution of one variable changes across the different categories of the other variable. It visually highlights potential associations or lack thereof.
Yeah, seeing it laid out like that would definitely help. Okay, finally then, when should we absolutely not use a chi-square test? When is it the wrong tool?
Definitely don't use it if your data isn't categorical, if it's continuous like height or time.
Yeah.
Also, if your expected counts are really low across many cells and you don't use a correction like Fisher's exact test, chi-square isn't appropriate.
Right, the small count issue again?
And also, if your observations are dependent, like if you measure the same person multiple times, those observations aren't independent, you need a different kind of test for that.
Okay, so clear situations where it just doesn't fit. Great, this has really clarified things. So the big takeaways seem to be, know if you have categorical data, figure out if you're testing independence or goodness of fit, and always check those expected counts.
That's the core of it. And what's really powerful, I think, is that that lets you put a number on whether a pattern you think you see in categories is likely real or just, random noise.
Yeah, it moves beyond just looking at percentages, doesn't it? It adds that layer of statistical significance.
Exactly.
It really makes you think, how often do we see potential associations between different groups or categories in everyday life or in our work? This gives you a way to actually test those ideas. Think about customer segments and purchasing habits or maybe treatment outcomes across different patient groups. It's a tool for digging into those categorical relationships. Something to ponder. Thanks for this deep dive.